All right, sequences and series. Despite just saying that we were in a rush, I am going to start this with a historical story that I like a lot, and it illustrates this principle. I'm pretty sure the year was 1787. There was a little boy named Gauss. Gauss was his last name. I forget his last name. And the legend goes that Gauss was sitting in his classroom, and his teacher needed to give all these little 10-year-olds busy work. This is a German classroom. It's a one-room schoolhouse. All the kids are in there. And he says, all right, students, I need you guys to add up all the numbers from 1 to 100. Yeah, just keeping them busy, right? So 1, 2, 3, 4, 5, ... all the way up to 96. Something I can't write. 97, 98, 99, 100. Okay? And apparently, Carl, that was his name, Carl Gauss, little Carl got up and started to walk. Or the teacher said, here, add up all the numbers from 1 to 100. And all the kids started to pull out their little chalkboards, because paper was expensive back then, and add it up. Yes, Nate, is this vital?
Would it be 5,000?
Stop. Don't say a word. You won't help. Okay, but you're on the right track. Okay, here's what happened. The teacher gives the assignment, turns around, starts to walk back to his desk, and supposedly he was only halfway back to his desk when little Carl raised his hand and said, excuse me, teacher, is the answer 5,050? And I know Nate heard this story 2 summers ago, actually for me, but the teacher was stunned. Now, my personal strategy at 10 years old, or even any age before I heard this story, would have been to start going 1 plus 2 is 3, plus 3 is 6, 10, 15, etc. And some people will do that slowly, some people will do that quickly. Everyone who does that, though, they're not really, they're all basically as smart, just some are faster or better at it. Here's what little Carl figured out at 10 years old. He said, what is 1 plus 100?
101.
101. What is 2 plus 99?
101.
What is 3 plus 98?
101.
How many pairs of numbers are you going to get from 1 to 100 that will all add up to 101?
50.
50. Because you're going to go from 1 up to 50, and from 100 down to 51. And when you meet in the middle, at 50 and 51, you're still going to have pairs of numbers that all add up to 101.
Oh, and you multiply that by 50? Or?
Yeah. So 50 times, you got 101 pairs, you got 50 pairs that each add up to 101. What is 50 times 100?
5,000.
What is 50 times 1?
50.
Excuse me, teacher. Isn't the answer 5,050?
That is great.
Is that so hard?
No.
That teacher was pissed.
Probably. He did not get his... The one version of the legend I read says he was going to sit down to write a love letter to his girlfriend. I don't think he got very far. Supposedly he didn't even make it back to his desk. Little Carl Friedrich Gauss, that was his full name, went on to invent many areas of number theory. And just how numbers behave.
This is a real story?
It's a story about a real guy. I wasn't there. I don't know if it happened. But Carl Friedrich Gauss was a real mathematician, and this is a story about him being 10 years old and being, yes, this smart at 10. That's the kind of guy who goes on to invent major areas of number theory. What Carl was doing, whether he knew it or not, was taking advantage of an idea called an arithmetic sequence. I am possibly misspelling arithmetic. Maybe one of those words that's spelled differently, like here in England, I don't even know. How do you, well, never mind, I'll see you later. An arithmetic sequence is a list of numbers. It's a list of numbers separated by a common difference. Difference as in subtraction. Difference as in sum, difference, product, quotient. Could also be addition, though. A list of numbers separated by a common difference. For example, 1, 2, 3, 4, 5, ... Is that an arithmetic sequence?
Yes.
Yes.
1, 2, 3.
What's the common difference between these numbers?
One more.
One more. One. Yes, Nate?
Isn't it an E instead of an A in arithmetic? Or am I just...
Probably. That's what I was actually thinking. I'm not 100% sure, but that's not. We're not really going to focus on that now while we're recording it, but I'll check it later. I should be able to check in your book, actually. But it is arithmetic. Very good, Nate. Okay. So this is a fairly simple common difference. Is this an arithmetic sequence?
Yeah.
What's the common difference?
3.
Okay. In this case, I would say D
We -3, right?
equals -3, yes. Those are two examples. Now from here, we need some notation. We need to be able to describe arithmetic sequences and series, and we're going to try and talk about another type today as well. So the notation goes like this. These always follow a pattern, and it should look a little familiar. If I write A sub n, this refers to the nth number in my sequence. Okay? A sub n refers to the nth number in my sequence, in my list of numbers. A sub n, if it's arithmetic, is always going to be a very set pattern. I'm going to go by what your book says. I used to do this differently. A sub 1 plus n minus 1 times the difference in the numbers. Okay? Nice shot, Diego. Okay, this D is your difference. This 1 is your first term. And this n is the number of the term that we are talking about. This A sub n is the nth term. Nth term, first term, number of the term we're talking about, and the difference between each of the numbers. Now this is only true for what's called an arithmetic sequence. There are other types of sequence, and they have different patterns. We're going to talk about two general types, and I'm just going to let you know that others exist. And we'll talk about some of them, but you're going to learn a lot about this one and one other one. Any questions on this notation? Nope? All right, I think you guys are ready for specific questions now. Let's find out. Okay. Given the list of numbers, the set of numbers, I should say, and I'm going to do this. I'm just going to give you this list of numbers, and I'm going to say it goes on for a while.
I've heard a whole bunch of questions like these in the SAT.
These come up on the SAT, but only as, they're not supposed to do anything in Precalculus, but they start asking you pattern questions about it.
Yeah.
And a lot of Algebra 2 and some even Algebra 1 books allude to this stuff.
Yeah, they have pattern questions, but there's nothing like...
I don't think they expect you to know this notation.
No.
There's a lot of previewing on the SAT.
Could you solve it without notation then?
Yeah, I was tutoring a kid who's already seen this on the SAT, and I reminded him of this, and he was able to
That would be...
do better. Okay, did I just write the first four numbers of an arithmetic sequence?
Yes.
Yeah.
Okay. What is my first term?
50.
Okay. What is my common difference?
2.
2.
-2.
-2.
-2. Thank you for catching yourselves. -2 is the common difference between them. Here's where this little formula comes in handy. What would be the 74th term in this sequence? In other words, what is A sub 74?
You definitely do see like this on the SAT.
Well, there's three definite ways to do this, okay? If you have all the time in the world and an incredible attention span, you should keep subtracting 2 and just count first term, second term, third term, fourth term until you get to 74.
Yeah, but you don't have much time.
Probably not on the SAT, that's not a good strategy. You could also say, if you started at 50 and you took 2 away from 50 74 times. Well, wait, would you take, to get from a sub 1 to a sub 74, would you take 2 away 74 times?
No.
How many times would you subtract 2?
It would be 70 times, right?
I'm not sure you're getting that one from.
Because
You're starting on a sub 1, so you don't count the one you start with.
Oh, 73.
73, that's right.
Right,
So you
right.
would subtract, so what's negative 2 times 73?
You would subtract that minus 50?
Yeah,
Okay.
that's like a strategy that would work. And that strategy, believe it or not, is this formula. Congratulations, Diego just re-derived this formula. Because the strategy Diego and I just talked about was that a sub 74 would be 50 plus, we're looking for 74, the formula says n minus 1, so if you're talking about the 74th term, you put in 74 for n, and our common difference is negative 2. So this formula says the 74th term is 50 plus 73 times negative 2, or 50 minus 146. Please double check me so that we're not all embarrassed on YouTube if that's wrong. I believe that's correct. I'm going to go on until someone corrects me.
Wait.
146.
73 times negative 2?
You're good.
That's
That means,
Yeah,
no,
yeah,
that
that's
looks
right.
right to me.
Keep double checking me, Remy, though, because you often catch that stuff. And 50 minus 146 is negative, what is it?
96.
Wait, do we use a
96.
calculator for this unit, or?
Some questions yes, some questions no. Probably a mixed test. This one I probably would not let you use a calculator on. Now, there's only one other thing I want to say about arithmetic sequences before I go on to another type of sequence to mention it. Believe it or not, you've done something almost exactly like this before. Okay? This is going to be a bit of a stretch, but I want to see if you guys can get it. This formula is very similar to one you've seen before. Okay? Where you have a result that is equal to some place where you started
Oh,
that's changing by the same amount every time.
the thing with the money. With not the money, what would be the... God.
There's a lot of financial examples for what I'm thinking about.
No,
The example I gave you?
exponential growth.
Oh, no, exactly wrong, but I know what you mean. So I compared this to exponential growth with something else, not like interest rates. Exactly different. It's one of them. It's actually simple interest. No, not really, never mind. I was about to say something dumb. Okay, but there's a result equal to something you started with plus something that changes by the exact same amount every time you go up one.
Velocity.
Velocity in physics, very good, but believe it or not, I'm going even simpler.
Jeez.
A result is a y value, and on a line, you get a y value because you start at one place on the x-axis, and you change by the same amount, which is slope, every time you go up 1 by x. So every time x goes up 1, you go up or down by the slope after starting at the y-intercept. This is slope-intercept form of a line.
Wow.
I really thought you were going to get it there. But v equals v initial plus at is
Yeah, that's what I
also
was thinking.
slope-intercept form. v equals v initial plus at is also you start at one velocity and you accelerate by the same amount each second. You start somewhere in the y-axis, you go up or down by the slope for each x interval. There's one difference with this though. You don't start on the y-axis, you start on x equals 1. That's the only difference with sequences in series. But it's a lot like slope-intercept form. You're going up by the same amount. Any quick questions on this? Going once, going twice. Okay. This is a sequence. Now we have to talk about something else. I have 2 words up here, sequences and series. A sequence is a list.
Should we write
What if it changes
The line example?
the y equals...
If it will help you remember it and you won't get confused between the fact that this is b is when x equals 0 and this a is when n equals 1, yes.
I'm just going to not write.
Okay, don't write it now. I'll try and tell you that a little more later.
What if it changes, like it goes from 50 to 48, then to like 40 to like 40, and then back to like
Gotcha.
38?
Okay. We're only going to look today at 2 types of patterns, at 2 types of sequences and series that follow very specific patterns. That will not come up today.
I don't know.
Tomorrow, the next day, we'll talk about sequences that can be anything. And you'll have to figure out the pattern of those. And they won't have as simple a rule set as this one. For example, once you know you're looking at an arithmetic sequence, then you can start talking about an arithmetic, which always looks wrong to me, series. The difference between a sequence and a series is an arithmetic series is the sum of n terms in a sequence. And this is where little Carl's trick comes in handy. It can be generalized, it turns out, as long as you know you're looking at an arithmetic series. Yes?
Is arithmetic mean part of this?
Yes. We'll probably get to that. Try and get to that today. Okay, sum of n terms in a sequence. Sum of n terms in a sequence. So this, for example, little Carl was asked to do. Gauss's first series. I feel like it's in his like baby book or something. Gauss's first series was 1, 2, 3, 4, 5, 6, ... 98, 99, 100, right? Okay? Simplest arithmetic series there is. What was a sub 1 in this series?
1.
Sequence, excuse me.
1.
A sub 1 is 1. What was the common difference?
1.
Positive 1. So, world's easiest one in the world. A sub n. Sometimes you don't even need to go through the formula to do this. Like if we go through the formula I just gave you, a sub n, I said, was a sub 1 plus n minus 1 times d, right?
Yeah.
So this, what is...
How do you use that if he wasn't trying to find any terms?
Well, hold that thought a sec. Yeah, this formula didn't help much. I just want to show kind of a funny point that may or may not help. What's a sub 1 in this series?
1.
1. And n minus 1 I'm going to leave. What's my common difference in this series?
1.
1, Diego says 3 on.
Yeah.
If I work this out, I get 1 plus n minus 1. A sub n just equals n. This is the world's simplest arithmetic series. This can be a trick question on a test. Kids struggle with this. But what's the 5th term of this sequence?
5.
The 6th term is 6. The 100th term is 100. The 1,000,000th term is 1,000,000. When I put this on tests and quizzes, sometimes kids really struggle because they think that can't be right. It has to be more complicated. But that's all it is.
Like the light year problem?
Like the light year problem in physics, right? How far does light go in 1 year? And the answer is 1 light year. I always get a range of answers on that. Well, here's what Gauss was doing. He realized that in this sequence, if you take the first term and the last term and add them together, you are going to be able to, and then you realize you have 50 pairs of them, you can find the sum. So that turns out to be a general formula. The sum of the first n terms in an arithmetic series equals n over 2 times the first term plus the last term, whatever term you want to go up to. So think about what little Carl did with his 50 pairs. He said, I have 100 numbers. If I divide that by 2, I'm going to get 50. The first number is 1. The last number is 100. So once again, he gets 50 times 101, or 5,050. According to legend, he figured out this pattern for these 100 numbers at 10 years old. He was a little bit older when he realized that this formula would work for any arithmetic series. So if the SAT asks you to add up, gives you an arithmetic sequence and says add up the first 20 numbers, the kids who know this formula are going to finish a lot faster than the kids who are going 2 plus 4 plus 6 plus 8 plus 10 plus 12, etc. Does that make sense?
Mhm.
I realize I should probably do an example here, but I want to try and cover a little more territory. And I've done just this one example here, the world's simplest one. Well, what was the second? Let me do one real quick. What was that second example I gave? What did I do, 50, 48, 46?
Yeah, 50, 48, 46, 44.
These get uglier with decimals and fractions, but
Are we ever going to add decimals and fractions?
I'll probably give you a calculator for those unless I make the fractions fairly simple. So this goes, I'm going to say this goes on like this for a while. If I say find S sub 20, first off that's the notation, I left that out over here. S sub 20, that means sum of the first 20 terms. Okay? Well, my formula over here says the sum of the first nth terms is n over 2 times the first term plus the last term. Hey, I see a potential problem here.
Last term is going to be zero.
No, well, no, it shouldn't be. I think I know what the last term will be. It's not hard to find in this series, but I know I'm looking for the sum out to 20, right?
Yeah.
So I know I'm going to put 20 over 2, and I know I'm going to put 50 in for the first term. Do I know my 20th term?
No.
No. These problems do get harder from this, but we'll start fairly simple. A sub 20, though, is a sub 1 plus 20 minus 1 times my common difference.
Is there a reason why we're using S now? Or is it just?
This is sum.
Oh, okay.
This is the sum. Oh, sorry, let me be very clear. This formula gives you the 20th term.
Right.
This formula gives you the sum of the first 20 terms.
Oh, okay.
This tells you what the 20th number in the sequence will be. This tells you what happens when you add up the first 20 terms.
Okay.
When you go from listing them to adding them, that's the difference between a sequence and a series.
Okay.
I can't.
Okay, let me make sure that's clear. This is my sum formula out to any number of terms as long as it's an arithmetic sequence. If you can't find, make sure that common difference exists. So you guys get that I need to find the sum of the first 20 terms. To do that, I need to find the 20th term. So that's going to be 50 plus 19 times negative 2, correct?
There are going to be problems where we have to use both formulas, right?
Yep.
Yeah, that's what
Oh, and more. You'll see. Okay, negative 2 times 19 is negative 38, I hope. Add that to 50, and I'm getting 12. So the 20th term is 12, but what was I asked to find?
Wait, wouldn't it be negative? Oh, right. So you subtract it from 50.
Yeah.
Right, you said add.
Well, I said add negative. I hope I said add negative 38. That's what I meant to say.
Oh, okay. I thought it was add 38 and then do so.
That would be different. Double check me. How am I doing?
You guys.
Okay. Remember, the question, though, was not find the 20th term. It was find the sum of the first 20 terms. Now, you can count out 50, 48, 46, 44, 20 times. But remember, this is the sum, so you'd be going 50 plus 48 plus 46 plus 44 plus 42. That sounds like less fun. So the sum of the first 20 terms is 20 divided by 2 times 50 plus my 20th term, which I just figured out is 12. So that's 10 times 62. So then I'm getting 620.
Oh, I thought we were done.
Pardon?
I thought we were done when we found 12.
No, that's the 20th term. That's what's going to be confusing for a while. There's a difference between finding the 20th term and finding the sum of the first 20 terms. Big difference. Two different formulas. That's your sum formula. I have it written and circled 2 places on the board, go me. You guys get the difference between the list, the sequence, and the series, which is what happens when you add them all up?
Yeah.
All right, I'm going to start talking about definitely one other type today. You have worksheets which I have handed out and which I've already emailed to you for homework, but I haven't decided which problems yet. May I erase this column?
Yeah.
Yes.
All right.
So is this all we're learning today, or?
Well, there's another type of
Oh.
sequence and series you're going to learn.
Thanks, Mr. Brown.
Anytime, anytime.
You can erase everything.
And a couple more terms after that. Geometric sequence. geometric sequence. Okay, geometric sequence is a list of numbers separated by a common ratio. These get trickier. List of numbers separated by a common ratio. Sometimes, though, they're a lot easier to see. For example, if I write 1, negative 1/2, positive 1/4, what's coming next?
What?
Common ratio. What does ratio mean?
If you mean negative 1/8?
Awesome, Danny. What's happening in between each of these? What comes after that?
Multiply by negative
Cutting
1/2.
Cutting it in half.
So it's become positive 1/16.
Awesome.
Negative 1/32.
Awesome. Let's
Positive
stop there.
1/16. Okay.
You're good. Okay. Separated by a common ratio means you're multiplying or dividing by the same thing, positive or negative each time. So for this one, I would say a sub 1 equals 1, and my common ratio is negative 1/2, because that is what I'm multiplying or dividing by each time. Does that make sense?
Yeah.
Some of these are really easy to see, some of these are kind of hard to see. Some of these will be tricky.
Sorry about that.
Sorry. The general form of a geometric sequence, if you're looking for the nth term, okay, Diego, this is going to resemble the interest rate ones that you're looking for, that you were talking about. This is, geometric growth is exponential. But it's the first term multiplied by that ratio n minus 1 times. Okay? So now I'm going to ask, what is the 15th term in the sequence given in this sequence here? What's the 15th term in this sequence? As much fun as Danny was having, I really don't want to go 1, 2, 3, 4, 5, 15 times with this. Might be fun. And I'll go ahead and tell you for some of the questions on the non-calculator part on the next test, I won't even care if you give me a specific answer. Here's what I want you to know. The 15th term of this sequence is the first term, which is 1, times the ratio, which Danny correctly said was negative 1/2, raised to the 14th power. And if it's something like that, I would expect you to... Actually, there's a couple things further you could tell me about this, but I don't expect you to figure out what 2 to the 14th is without a calculator.
Wait, it's not 36. It's
32nd. Thank you for catching that before I uploaded it. Very good. That's what I get for listening to you guys. The weird thing is you went correctly from there to 1/64th when you said it, didn't you? Yeah. So you must have, okay. And I was just writing down what you said. Just out of curiosity, what could you tell me about the 15th term? How could you simplify this a little bit? Let me ask you this, is it positive or negative? What happens when you raise something negative to an even power? It's positive, very good. Because if you raise something negative to an even power, it's going to be positive. What's 1 times anything? Itself. And what's 1 to the 14th power?
14. Or 1, wow.
Wow, Danny, okay.
I went from really
If
smart.
I had time, I would edit that out. Wow, that was quick. All right. So I know that this could be simplified to 1/2 to the positive 14th, and I know that fraction would be positive. So I think it'd be fair for me to ask you to simplify it that much without a calculator, but I really don't want you to know. I don't care what 2 to the 14th is without a calculator. But I know that that's what the 15th term of this sequence is. Okay? Any questions on that idea?
Just move.
Geometric sequences are often easier to spot. Okay, I have a slightly ambitious plan for the next 15 minutes. Are you ready?
Please do not erase.
I want to erase column 2.
Alright.
May I start erasing column 1?
Yes, you can erase column 1.
Okay. As annoying as that was,
There's another more
we're going through 2 more layers of annoying if I have time.
Oh.
All right, that's the plan. Maybe I may have to go a minute or 2 over. Apologize, but okay. What's the 15th term of the sequence? What if I said I wanted you to add up all the terms of that sequence? Would you have fun by hand going 1 plus negative 1/2 plus positive 1/4 plus negative 1/8? First, you have to find a common denominator. I'd like to put all that over 2 to the 14th. That would be annoying. All right, now, there is, for a geometric series, what's the difference between sequence and series? Sequence, what are you doing? I know it's unfair, I just gave this a few minutes ago, but what's the difference between sequences and series?
A sequence is finding a number in series.
Yeah, sequence is, you have to write it here.
It's finding a number in the series, and the series is adding up the value of all the numbers in the sequence.
That was so good to put one word. You're finding one of the numbers in the sequence. You said finding one of the numbers in the series, but series you're already adding it up. Right idea. The sequence is actually just the list of numbers. And questions about sequences, like Tim said, is just finding one of the numbers in the sequence. The series is when you're adding them all up. Some years like to prove this rule. This year we're a little short on time. So I'm just going to tell you
That is true.
that's true. One day I will probably do a proof of one of these. The sum of the nth term of a geometric series is... See, I usually see this written differently. The first term minus... All right, the first term...
Safe space and time are writing things like G series, and I feel like
Yeah.
behavior and people are kind of like kicked out.
I'm changing it slightly from how it's written in the book. That's why I learned it. Good enough for you. Yeah. Changing it slightly from how it's written in the book. It's the first term times 1 minus r to the n over 1 minus r. Now, unfortunately, I've erased it, but a minute ago in your notes, we were looking at the sequence 1, negative 1/2, positive 1/4, etc., right?
Right.
So a sub 1 equals 1, and the common ratio, Danny said, was negative 1/2, and we all agreed, correct?
Correct.
Okay, so now, like Tim said, we've gone beyond just listing these things, and we have gone to summing them up. So if I said, what was the sum, what did I say, 15 terms? The sum of the first 15 terms is a sub 1, which is 1, over 1 minus negative 1/2 to the 15th power, divided by 1 minus negative 1/2. How am I doing on this one? Have I filled that in correctly?
Yes.
Assuming I've written the formula correctly, that should be filled in correctly.
Yes, I think.
Okay, here's how this gets a little bit exciting. Let's start seeing what we can do with this. You probably can't get an accurate answer. A precise answer, I should say. Start on the top. What can you tell me about 1/2 to the 15th power? Like we did last time. Is it going to be positive or negative?
Negative.
Negative. And 1 to the 15th?
1.
Danny, redeemed yourself nicely. And then 2 to the 15th will be...
Something large.
Don't even care. All right. 1 plus 1/2 is 3/2. Subtracting negative becomes positive. So it looks like my sum is going to be 1 minus 1 over 2 to the 15th over 3/2, which is 2/3 times 1 minus 1 over 2 to the 15th. How big is 2 to the 15th?
I would say it's about 32,768.
About, there you go.
About
You're pretty subtle with that calculator, buddy. And if you put 32,000 whatever on the bottom of a fraction, how small is that fraction?
pretty small.
Right? This is getting pretty close to 0. In fact, I would say the sum is pretty close to 2/3. Does that idea sound familiar?
Yeah.
All right. What is that idea like? We're talking about end behavior, limits, that sort of stuff?
Yeah.
Okay. So this sum is really about 2/3, but I'm going to leave it like that. Any questions on using this formula? I realize I presented it without proof, but
Can you prove it?
I have before, but not right now.
It's possible.
Yeah, well, it's been proven, yes. There's nothing in here that isn't proven. There are some math ideas that haven't been proven. They don't make it into high school textbooks. They're pretty highfalutin at this point. Highfalutin, I believe, is the technical
So
term.
everything we learn, it has been proven.
Yes. Can I prove it all? No. Can I prove some major chunks of it that I'm not going to share with you because it's not the best use of our time? Yes. Okay. Some of it I honestly don't know how it's proven, but at this point I trust some people. All right.
Do not erase column 2.
I will not erase column 2.
Please erase column 2.
Is it hurting your brain? All right. Okay. Over here, very specific example of infinite.
Oh, fuck. I hate that word now.
Okay. Geometric series.
Oh,
Do I have some editing to do, Tim?
that feels terrible. No, it's just that sounds so horrible.
Infinite geometric series. You've heard an example of this. One more story that will make this relevant a bit. I'm probably going to misquote it. I didn't prep for this one as well. Well, there's something called Xenos Paradox. Have you guys ever heard of it?
Sounds painful, but no.
Give the short version. You heard about it, I think, from me 2 summers ago. Nate's hearing some of this for the second time. Xenos Paradox is the idea that I can never leave this room, or more specifically, this marker can never reach the board. And the idea behind Xenos Paradox, well, the idea behind it is, in order for this marker to reach the board, first it has to cover half that distance, right? Then it has to cover half the remaining distance. Then it has to cover half the remaining distance.
Oh, so
Then half the remaining
just
distance.
keep on growing by
Well-
a tiny amount.
Exactly. And the idea behind that,
It's like an asymptote. It can be closed, but it won't touch it.
right, and asymptotes we now start talking in terms of limits, so I'll get there in 1 sec. But the idea behind this was, suppose there was an argument that the Pythagoreans and the other ancient mathematicians of ancient Greece must be full of it because, if their math was correct, it would lead to the idea that you have to cross an infinite number of intervals just to leave a room or just for an arrow to hit a target. And if you have to cross an infinite number of intervals, how can that add up to this finite distance? And even an infinite number of intervals should take an infinite amount of time intervals to cross.
So then they came up with the word paradox and slapped it on.
Well, it was Xenos Paradox for years, but obviously markers can reach targets, okay? Arrows can kill people. Archers don't kill people, arrows do, right? Something like that. Okay, so...
Guns don't kill people, the NRA did.
Stop. I have to post this online. Okay, now, shouldn't have gone there. Infinite geometric series. Okay, so Xenos Paradox is the first recorded example of this. And what Zeno was saying was, how can half of a distance plus a quarter of a distance plus an eighth of a distance
16.
plus a 16th of a distance plus ...
34.
equal anything finite? How can that happen? If you start out with something with an infinite number of them. But here's what we were actually talking about. If I take away the plus signs,
Wait, is that about to say infinite or finite?
finite equals something finite. How can this infinite number of fractions add up to something finite? So if I take away these addition signs and put commas in between, we will be looking at a sequence. Will we be looking at an arithmetic or a geometric sequence? Geometric. We are not adding or subtracting the same amount each time. We are multiplying or dividing by the same amount each time. This is a geometric sequence. Or it would be a geometric sequence if it has commas. If instead of listing the numbers, you are adding them all up, it is no longer a geometric sequence. It is now a geometric series. That's the difference between listing them and adding them. A series is when you add them all up. I just wrote a formula for the sum of any geometric series. What is that formula?
S equals
A sub 1, the first
A
term,
times 1 minus r to the m
right?
over 1 minus r.
Over 1 minus r. Okay. So, let's find a general formula for the sum of any number of terms you'd like in Xenos Paradox. S sub n. What's my first term?
1/2.
Okay. And what's my ratio?
Negative.
You're thinking difference. What's my ratio? What am I multiplying by at the same time? Every time?
1/2.
Positive 1/2. That's being raised to the nth power. And that's 1 over my common ratio, which is 1/2. Because, just to be clear, my first term is 1/2, and my ratio is also 1/2. I'm multiplying by that every time.
I hate fractions within a fraction.
We'll get rid of them then. I'm going to move up here for this step. 1/2. 1 minus, okay, what's 1 raised to any exponent?
1.
1, okay? 2 raised to that power is going to be 2 to the n. What's 1 minus 1/2?
1/2.
That should have been everybody. Diego's dominating this conversation. All right, Diego says he doesn't like fractions within fractions. Yeah, what happens if I have 1/2 on the top and 1/2 on the bottom? Bye-bye. See you later. So this becomes 1 minus 2 to the n. Nope, it doesn't. This becomes 1 minus 1 over 2 to the n. That would be very different. Okay, without knowing it, here's what Zeno was talking about. He wasn't talking about some number like this that can never actually reach 1 because there's always some fraction there. What he was actually talking about was the limit as n approaches infinity. Remember this notation? Of 1 minus 1 over 2 to the n. Now remember, I said a limit. It's where you're headed, but you don't care if it gets there at this point in your lives. But it's also like a dog on a leash. Okay? If you let the limit, if we let n be infinity here or here, that might be confusing. But if you rearrange the problem a little bit, you get to a point where letting n reach infinity is not problematic at all. We wait till this last step and we say, okay, what happens if this n, that's what this asks, what happens if this n gets as large as we can imagine? What happens to 2 raised to the largest power you can imagine?
We stop caring about the fraction. We're just going to get so close to 0.
Right, the denominator gets even more huge than we can imagine, which means if the denominator is huge, the fraction is as small as we can possibly imagine. What's the smallest thing you can imagine?
0.
0. So this limit equals
1.
1.
I'm starting to get limits.
All right, so
Wait a minute. Isn't it 1 minus undefined? Because when number over 0 would be undefined.
this isn't over 0. Again, this is.
Oh, you're making it's getting infinitely closer to
Yeah.
0.
If
Okay.
this were, if n were, well, if n were
Wow.
approaching 0, this would actually be approaching 2 to the 0 is just 1, so that's something else. But yeah, if this whole expression was getting as small as you could imagine, yes, we'd be heading towards undefined. Excellent. Good memory. Not
I'm
great
gonna
at reading the difference between
Is this Xeno guy is the coolest name ever.
That is a cool name. But the implications of this are fascinating to me because the implication of this is 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64, etc. really does add up to 1 if you got an infinite number of times. It's the craziest analogy, but it came to me one day and it helped one of my classes. Imagine a sock drawer. And the first sock is huge and it fills up half the drawer. And the second sock fills up half the remaining space. And the next sock fills up half that space. And the next sock fills up half the remaining space again. You can fit an infinite number of socks in that finite drawer as long as they keep getting half as small each time.
But
Which is kind of a crazy idea.
soon enough, won't it get so small that...
Well, if you're talking about actual cotton fibers, yes, there's a point. When you're talking about actual molecules of cotton, yeah, my analogy breaks down in the real world at that point. But In math, we don't have to worry about it because this is infinitely divisible. The arrow does reach the target, or as the bad math joke goes, an infinite number of mathematicians walk into a bar. The first one orders half a pint, next one orders a quarter pint, next one orders an eighth of a pint, next one orders a 16th of a pint. The bartender says, "You're all idiots," and puts one full pint on the bar. Because that will feed all infinite mathematicians if they keep all taking half as much. It will all add up to 1.
Until one of them is just like getting microscopic.
Again, if you look at actual molecules, there comes a point where you can't subdivide. But Xenos Paradox is your first example of an infinite series. What we're going to do is we're going to continue to look at arithmetic, geometric, and infinite series together over the next tomorrow.
Over the next,
And, over the next for an infinite number of days, divided into infinitely small increments.
Oh my god, I would.
But no, we'll look at all 3 of these again tomorrow and go into a little bit more depth. Nate, tomorrow we'll talk about arithmetic and geometric mean. Any questions on any of this real quick? Okay, homework tonight should be fairly simple and straightforward. It's on some worksheets. I'll give them to you now.